class, we got you. Wherever you want it from, we got what you need. Today online class.
Good day, viewers all over the world. You are welcome to Toydell online class. Today we want to look at the normalizer of a subgroup. The normalizer of a subgroup. So in our last class, we talked about a normal subgroup. And we define a normal subgroup as a subgroup. Is that we call it normal subgroup or an invariant subgroup? Is a subgroup in which the right coset is equal to the left coset. That is, if you have, we know the definition of coset, where G is the element of a group, N is the subgroup, is equal to NG. So when we have a normal subgroup, it simply means that it's a subgroup in which the right coset is equal to the left coset. So today we want to look at the normalizer of a subgroup. Before the normalizer of a subgroup, we are going to give some assertions. So now let's go. Let A be an element of a group G. Let A be an element of a group G. Then the normalizer of A in G is denoted by N of A and given by N of A is equal to X, such that X belongs to G. A is equal to X inverse. And that's what we have. Now let's look at this. Let A be an element of a group. That is, A is an element of a group. And of course, if we say a group is a subset, is a non-empty set with a binary operation. So A is an element of that group. Let A be an element of a group G. Then the normalizer of A in G is denoted as this. The normalizer of A in G is denoted as N of A. And it's given by N of A is defined as X, such that if you pick an element X apart from A in that group that belongs to G, A is going to give us X multiplied by A X inverse. And of course, we know that X inverse is going to give us identity. Because just like when you say X multiplied by 1 over X, at the end of the day, we are going to get 1. So X inverse will give us identity. It's going to give us identity elements. So that is the definition of a normalizer of a group. But we want to talk about normalizer of a subgroup. Then now let's define the normalizer of a subgroup. Definition. Let G be a group. Let G be a group, and A a subgroup of G. Of course, A is a subset of G because a subgroup is a subset of a group, and A subgroup of G. So the normalizer of A in G, is NG of A, and is defined as, if for every G that belongs to G, we can have G inverse, which is equal to A. Now let's look at in this case. Now this is the definition of a normalizer of a group. They want to talk about the definition of a normalizer of a subgroup. Let G be a group. G is a group, and A is a subgroup of G. Of course, if A is a subgroup of G, it simply means that A is a subset of G. So the normalizer of a subgroup now, A in G, is defined as NG of A. is defined as G, where G is an element of the group. So the element will now be, when we operate the element, both at the left and the right. At the left, the normal G. At the right, we have the G inverse. The inverse of G is going to give us A. And that is the definition of a normalizer of a group. That's the definition of a normalizer of a group. From the word the normal subset, the normal subgroup is when we have the left coset to be equal to the right coset. That's the definition of a normal subgroup. So we are talking about normalizer now. How do we stabilize? Just like a stabilizer of a subgroup. So this is the definition for normalizer of a group, and this is the definition for normalizer of a subgroup. So please let's note that G, which is an element of a group, if we multiply by A, which is the subgroup, multiply by A inverse of an element of a group, is going to give us A. And that is the idea behind the normalizer of a group. Now let's take example. Let's take example on normalizer of a group. Let's take example. Oh, I'll call it exercise. Let's take example. Show. We have to show that the normalizer of A in a group, the normalizer of A in the group G, that is NG of A, is the normalizer of a subgroup in a group, which is defined as G such that G belongs to the group G inverse is equal to A. The normalizer, we have to show that the normalizer of A in a group G, defined as what we have on the board, is a subgroup. It's a subgroup of G. So how do we show that? Of course, for that normalizer to be a subgroup of G, we have to show all the properties of a group. That is what is expected. For us to be able to show that, we must show all the properties of a subgroup. We have to show all the properties of a group. So in this case now, we must first show that the first thing that is needed there is for us to show that that subgroup, that G, this group and subgroup is non-empty. That is the first one that we want to show, is that we want to show that the group and the subgroup is non-empty. It's non-empty. So we show that it's non-empty. How do we show that? We said since E belongs to G, this is identity element. Identity element belongs to any group or subgroup. Of course, any group or subgroup must have identity element. We have said at the inception of the course that every group that we talk about in a group must be non-empty. So if a group has at least one element, it has an identity. So since E belongs to G and E inverse is equal to A, of course, this is the idea behind the normalizer of a subgroup. That is when you pick an element, this element E is coming from G. Related with is the subgroup, then E inverse must get A. And that is the idea about a subgroup. That will give us that. Then this implies that E belongs to the normalizer of a subgroup. Every subgroup is a subset of a group. So if E belongs to a group, it simply means that E will belong to the subgroup of that group. That finally, it implies that the normalizer of the subgroup is not empty. That's the first thing that we show. That is the first thing that we show. That the normalizer of the group is not empty. That is, it has at least one element. So that's the first thing that we show. We want to show, this is what we want to show. We want to show that this normalizer is a subgroup of a group. So the first thing that we have shown now, we have been able to show that that normalizer is not empty. That is, it has at least one element. It's not empty. So that is the first thing that we show. Then we go ahead and show the closure property. So we go ahead and show the closure property. That is, We want to show the closure property. In this case now, how do we show the closure property? At least, if you have two elements from that normalizer of a group, we can say let X, Y be elements of the normalizer of a group A. This implies that if X and Y belongs to the normalizer of a group A, it implies that X inverse and Y inverse must be equal to A. That is, this is the normalizer. Of course, we have been in the definition. We are able to see that G inverse. Excuse me. Here, G inverse will give us A. That is the idea behind it, and of course, it's logical. If this G inverse simply means 1 over G, then this can take care of this. We will be left with A. So if we want to show the closure property, we can actually have that assertion that we have on the board. We can have that assertion. Then if you now pick the two now, if you pick X, Y, the combination of the two now, the same thing as if you now pick X, Y, the same thing as saying X, Y all inverse. We are still on the same page, and this is going to give us, if we pick this, the same thing as you saying X, Y, A. I can start to split this to be Y inverse, X inverse. There's no problem. It's just indices. If X, Y belongs to the normalizer of that subgroup, we have been able to show that this and this will give us A. Okay? Then if you now pick the product of the two, we pick the subgroup, then the inverse of the product of the two. It can be expressed as what we have on the board. Of course, when you have X, Y, all inverse, the same thing as X inverse, Y inverse. It's still the same thing. Then I can interchange. It's allowed. So what I have on the board actually holds. So from there, we can have it that from there now we can have it that, you know, I can X and X inverse can actually give us the identity. That is, this simply means that what I have in between here can give me A from here. Please look at Y inverse will give me A. So if I consider everything together now, I'm going to have X inverse. That's what I'm going to get. Because Y inverse is equal to A. And if that is the case, then what is X inverse? It will be A. That's what I'm going to have. That's going to be A. Then therefore, XY belongs to the normalizer of the subgroup. That's what we have been able to show. So it shows that the closure law, the closure property or the closure law holds. So out of the 4 properties that we are expected to show, we have been able to show 1. So with what we have on the board, it shows that the closure law or the closure property actually holds. From this definition, this is the meaning of a normalizer of a subgroup. So it's like neutralization. We try to neutralize this. We just try to rewrite A in another form. Look at Y inverse is same thing as A. So when I look at what I have here, I will reduce this to A. It's logical. Then this also is equal to A. X inverse is equal to A. So that simply means that X inverse actually belongs to the normalizer of that subgroup. So we've been able to check the closure property. We move to the next property, the third one, associative property. Let's move to the third property. So if you're able to show all the 4 properties, then we can generalize that the normalizer actually belongs to a group. So let's go to the associative law. That is associative property. You know, in this case now, we are going to have 3 elements. We can say let X, Y, and Z belongs to the normalizer of the subgroup. This implies that X, Y, Z belongs to the group. That's the implication. Why? Because NG of A is a subset of a group. Every subgroup is a subset of a group. So every element that you have in a group automatically belongs to that subgroup. Every element that you have in a subgroup automatically belongs to that group. Okay, that holds. Then this implies that XY into bracket Z or W. We use that. So Z says Z. XY into bracket Z is same thing as X into bracket YW in G. In G. That is this is W. Of course, this is the condition under associativity. You pick the first two elements. You relate with the third one. Are you going to get the same thing as you picking the first, then you relate with the second two? If yes, then it shows that associativity actually holds. So from what we have on the board, this implies that it implies that XY of W, which is same thing as X into bracket Y of W in G, in NG of A, also holds because NG of A is a subset of G. Therefore, you can generalize that the associative law holds in the normalizer of the subgroup. So we can generalize that the associative law holds in the normalizer of that group. So we go to the third one, the third properties, which is the existence of identity element. So let's take the third one. Let's check for the third one. That is existence of identity. That's existence of identity element. So let's check if we'll be able to get that. Then this one is straightforward. Since identity element A, identity element inverse is going to give us A from the definition of normalizer of a subgroup, it implies that the identity actually belongs to the normalizer of that group. This one is very simple and straightforward. Of course, I've said it that it's just when we have G inverse, it simply means that this is the same thing as G inverse can be 1 over G. Of course, this can take care of this. We are going to have A at the end of the day. So if you follow that order under identity elements, under this identity, the third properties is very simple and straightforward. So we can actually show that it's very simple and straightforward. Then we go ahead and check for the fourth property, existence of inverse element. So how do we check that? We say let G belongs to the normalizer of the subgroup. This implies that G belongs to that group. Then there exists G inverse that belongs to that group. Okay, so G inverse, that is this an element, this is inverse of that element. He said or G inverse G must give us identity. When we look at under existence of identity element, when we pick an element, we relate it with the inverse. We must get identity element. That must be the standard. So if we want to find the inverse element, when we pick an element in the group, we relate it with the inverse of that group. We must get that identity. So also in this case, if we let G to belong to the normalizer of that subgroup, it implies that G belongs to that group, because every element of a subgroup automatically belongs to that group. Then if G belongs to that group, that simply means that there exists G inverse, the inverse in that group. Then we can make this assertion. So this assertion actually holds. So this implies that G inverse is equal to A. So that is the implication. It implies that G inverse is equal to A. Then what can we do here? We can also say that let's take G inverse of both sides. G inverse will be equal to what? G inverse A. Then from there, G inverse G inverse of G is identity. A G inverse is going to give us G inverse of A. Then from there, if we now multiply through, and this implies that from here, from what we have here, it implies that AG inverse is equal to G inverse A. From here, this is a neutral element. So AG G inverse is equal to this. Then this implies that we can have AG inverse G to be equal to G inverse AG. We are just trying to rewrite everything. Then from here, this implies that G inverse G is identity. It's same thing as, what do we have here? This same thing as G inverse AG. Then identity is neutral. Identity element is neutral. So A is equal to G inverse AG. If this is equal to this, it's equal to G inverse AG. And if that is the case, we can make the generalization and say if this is the case, A is same thing as G inverse of A. Then we can say, we can actually rewrite this. We can rewrite what we have on the board. We can actually rewrite this and say this implies that G inverse of AG that we have here, G inverse of AG is equal to A. So if I now take G inverse of AG is equal to A, then I can rewrite this and say G inverse of A. What is this G? I can write G and say G inverse into bracket inverse. When I say G inverse into bracket minus 1, it simply means that 1 all over G, the reciprocal. I want to take the reciprocal again. Then automatically it's going to become G. So G, we can write G as G inverse into bracket minus 1. We can write this, which is equal to A. If that is the case, it implies that G inverse belongs to the normalizer of A. So we are just trying to rewrite this in such a way that we are going to have something in the form of G inverse A G inverse, just like when we say G A G inverse. That's what we are trying to rewrite, and we have been able to do that. We can now conclude that thus, for all G that belongs to the normalizer of the subgroup the inverse G inverse actually belongs to the normalizer of the subgroup. Then finally, we have been able to check for all the properties of the group. Finally, we can say, therefore, the normalizer of A is a group. And that is what we are asked to do. So we can actually finalize and say the normalizer is a group. So, and that's what we are asked to do. So apart from the normalizer, we can have what we call, we also have what we call the centralizer. Let's just divide the centralizer before we call it a day. Apart from the normalizer of a subgroup, we can also have a centralizer. If you can lay your hand on standard textbook on algebra, you are going to find some of these concepts there. And it's possible for some of you to continue with algebra at the higher stage. So just put your mind there and develop interest in algebra. So let's briefly talk about centralizer of a subgroup. Let's briefly talk about it. So let's first define the center. The center of a group G, denoted by CG. In case of normalizer, we call it NG, N subscript G. So in case of a centralizer now, it is C subscript G. This is just a naming ceremony. We are trying to give the definition name. So CG is the set of all X that belongs to G, such that XG is equal to GX for all G that belongs to G. That is, the centralizer of a subgroup is defined as X such that X belongs to the group, and for all XG we can get GX for all G that belongs to G. So this is what you are trying to say. This is what you are trying to say. You know, this property actually comes up under the normal subgroup or trivial subgroup, where we said, you know, this is the right coset is equal to the left coset. So please check my videos on cosets and index. So we make some definitions there. So if you know if we are talking about the centralizer of a subgroup now, the center of a group G, denoted by CG, is the set of all X that belongs to G, such that XG is equal to GX for all G in X. You understand? Then that is CG is defined as this. Okay, that is the definition of the center of a group. That's the definition of the center of a group. That is, CG is the set of all elements of G which commute with every element of G. That's just the definition. Then what is the definition of centralizer of a subgroup, which is the last concept that we discussed? We can say let G. This is just the definition of a center of a group. We are about to define the centralizer of a subgroup now. Under the definition, let G be any group, and A as subgroup of G. The centralizer or the center of A in G, that is the centralizer or the center of A, which is subgroup of G in G, is the set denoted by CG of A and given by CG of A is given as for all G such that G belongs to the group and GA is equal to AG for all A that belongs to the subgroup. So this is the definition. This is the definition of the centralizer. So let's look at the definition of a centralizer. There's a big difference between this and the normalizer. In case of the normalizer, we have G inverse to be equal to A. So this actually normalizes the group because G multiplied by G inverse, it will be neutral. Then we are going to get A. But in case of centralizer now, if you have to define the centralizer of a subgroup, the definition is that we must have a group. Let G be any group, and A the subgroup of G. Also under normalizer, it's still the same thing. We have a group, and A is the subgroup. Then the centralizer or the center of A in G is the set denoted by CG of A, and it's given by the set is given by CG of A is given as for every G such that this G is coming from the group. If you have GA, which is equal to AG for all A that belongs to G, this condition, of course, is just telling us that the left coset is equal to the right coset. If you check my video on coset, because this G is an element of the group, while A is an element of the subgroup. And of course, you know how to find either left or right coset, and you know how to find the index, which is the distinct value that we get. So this is the definition of the centralizer of a group. So I'm going to stop here because of our time. We continue from there some other time. Thank you, and God bless you all.